Let's press the button. Hey everyone, and welcome to another week of AScript smart contracts programming. So as we talked about, I think about 2 weeks ago, so we covered all the basics, how to write one, how to test, how to deploy, how to verify, and then how to integrate with UI. So we covered all the pretty much the basics, and now you can not only build a full smart contract, but you can also integrate it with your apps, like web apps through some hooks we provide. So about 2 weeks ago, we're starting to pivot a little bit to talk about all the different use cases. So one of the biggest use cases, categories of ones that's involved, which we cover today, is called elliptic curve cryptography. So how many of you have heard about know about a little bit, at least heard about the elliptic curve? Points addition. Okay.
Yeah.
Okay. So what's the general impression? Like what is a elliptic curve to you? In at least in the context of Bitcoin.
A way to do the cryptography with private keys. No.
Yeah, that's one use case. You can have asymmetric keys derived from you can have a private key and then you can generate the public key, right? Okay. Anything else that's almost used daily or using pretty much most of, if not all, the Bitcoin transaction today? What is another thing you guys can think about? So once you have keys, what do you do usually with it?
Sign transactions.
Yes, correct. Yeah. So elliptic curve cryptography, usually when you talk about cryptography, there's two aspects. One is about the secrecy of it. This is a subfield of so-called asymmetric key cryptography. So basically you have instead of have one key, a sender and receiver share, you have two keys. Each party has two keys. One you keep it private, the other one can be made public. Okay. And so encryption and decryption, that's one big thing. But the other big thing is also what you just mentioned, digital signature schemes. So which we're going to cover a little bit. But before that, and because this is a big type of use case, so we are going to go from the basics. Okay, so if you already know that, you don't have to follow the beginning. You can skip a little bit later. So for people who have not heard about the elliptic curve, so basically you can think about, is again on the 2D dimension, you have x-axis and you have y-axis. And this is what elliptic curve, that's also what the name derives from, right? So it looks like the shape is a little bit, for now, let's talk about real numbers. So, we don't talk about so-called field and integers. So elliptic curve is all defined by this equation, right? So you have x coordinate, you have y. So if you fit in this equation, x any point, then you are on the point is on this curve, okay? So and the curve, sometimes it looks like the shape, like this shape, right? So this is the equation that describe it. And you can see from here, it's not hard to see. It's symmetric, right? Along the x-axis because, y is denoted as square, right? So if you have a minus y, negative y, you also get the same number after you square it, okay? Any questions so far?
No, good.
Okay, good. So once we have an elliptic curve, we usually can define, some kind of a arithmetic on top of it. I mean, I think today I'm going to, be a little bit of a, let's say, relax on the mathematical things. I just want to give you more intuition. So I'm not going to tell you what is a field and what's a group. Okay. So basically, you can think about is we are dealing with instead of real numbers like 1.5 or even pi, we're dealing with big integers. Okay. So end of the day, it's all integers because that's what the computers are good at to deal with. Okay, so first operation we define, in this group, you can think of, let's say you have two points, right? So you have a point P and then you have point Q. So you want to define, so-called a point addition. I mean here, of course, when I say addition, it's just reuse the addition when you add, let's say, two integers. But you can almost think about it as like overloading, right? In programming terms, it's not actually just add two numbers, right? Because this is the coordinate. This is the two coordinates, x and y. This is another x prime and y prime. You cannot just add them. So you have to, use this formula. But what this basically says is, so if you use show this graphically, geometrically, you can say, hey, if I have P and Q, if I want to add them together, how do I get the R here? So basically you connect these two, it's going to meet this curve, cut this curve at a third point, which we call which is the opposite of R, and then we reflect it along the x-axis, and that's how we get the addition of two numbers. Does this make sense so far? Point addition?
Yeah, without taking into account all the mathematical details, but yeah.
Okay. So, we just talk about high-level intuition, but if you really want to get into details, okay, so, that's how because this is you can use the math and all this, and the previous equation, you can derive actually mathematically what this number is given these two. Let's say this is x1, y1, this is x2, y2. And then, if you do the math, you can derive, R, this is x3 and y3. So this actually defined by this new equation. Basically you derive x3, y3 from y1, from x1, y1, and x2, y2. So this is the formula. You're going to derive the new points, okay? So, it's about, have this lambda, and this lambda is calculated in this way. So here, actually, you have two ways, right? So one is, hey, what if P and Q, they're different, right? This is the normal way you do it. But what if P and Q is the same point, right? Basically, you want to double. You want to double a point, right? Let's say P plus P. So then you can say, hey, now you cannot use the connect 2 points, right? Because that's just 1 point. So it becomes just the tangent. The tangent, and then it's also going to intersect with this number. And then if you do the math, you use a different formula, okay? Because otherwise, this is going to be 0, right? Because x1 is the same as x2, same for y2 and y1. So this is the graphical interpretation, and this is the exact math formula, okay? So basically, when you want to add two different points, you use this formula. And when you want to add two identical points, basically you want to double a point, you use the formula here, okay? Yeah, we're not going to derive the formula here because this is we just want to give the high level idea, okay? Make sense so far? This?
Yes.
Okay, nice. So once we have addition, a natural, extension would be, hey, what if I add, the points n times together, right? Because it's like any basic arithmetic. Once you have addition, a natural way to extend it would be like multiplication, right? This is so-called a scalar multiplication. So basically you use a point, but you are not multiplying with another point. That's not defined. So you multiply with a scalar, basically a number. So what this means, you say n times p, you pretty much do the addition, right? Point addition n times, okay? So again, as the animation here says, if you want to a plus a, then you can keep doing this, a plus b and b. You can keep doing, basically you keep doing this, right? So let's say, how do you multiply a point by, let's say, n times, what's the most straightforward way? How would you do it? Let's say brute force, using brute force, the most naive way. How would you, if you already have addition defined, right? Either for the same point or different points, how would you do a scalar multiplication? How would you do it?
So when you mean brute force, you mean like with pencil and paper and start doing it?
No, I'm saying is, let's say, how do you compute, let's say, 100 times p? If you only know, how do you do addition? How would you do it, the most straightforward way?
With a 4, like the one on the right side. So doing summing n times that.
Oh yeah, I kind of give out the clue here. Okay, I should put it on next.
Yeah,
But yeah, the naive way would be you just add it, do the addition 100 times, right? Let's say 100 times p, right? You do addition, 99 times, okay? But that's not the
yeah,
most efficient, right? What if the n, in our case, right? This is usually we are talking about Bitcoin, and the key space is usually 256 bits, right? And then if you say, hey, let's add 256, 2 to the power of 256, and then multiply p. You're going to do a 200 in the order of 2 to the power of 256 times, which I don't think you have a computer to do that at home, okay? So that's why we have to use more efficient way, right? So, if you do any kind of like math before, you probably heard about this double and add. So basically, for example, right, if you want to, let's say, compute, for example, 20 times p, right? You don't add 19 times. Instead, you first compute 2p, then you double it to 4p, right?
yeah,
And then once you have 4p, you can do the 8p and then 16p. So once you have 4p and 16p, you can add them together, which give you 20p,
yeah.
right? So
So
in
yeah,
this, you're doing much less calculation than you would rather you would do it natively. Make sense?
yeah, yeah, yeah.
So you only have to do like so using the computer term, like a logarithmic complexity, right? Instead of do linear in terms of n, right? So this is the algorithm we showed on the right here, pretty much. You can say, hey, the double and add, if you want to compute n times x, you don't want to just multiply it n times, pretty much. You can compute, x to the power 0.1, x to the power of 2 and 4, and such that. And then depending on whether the bit is set, if it's set, you can just add to the final sum. And then when you are iterating all the bits in binary format for n, so you get the final sum. Make sense so far? Okay.
I think so. Yeah.
Yeah. Okay. Yeah. For if you've done any kind of like programming, this is probably one of the most famous algorithm you can use to get you to more efficient calculation. Okay. So after we have this, so now I talk about point addition and then point multiplication. So here's the thing. The good thing is, it's all basic arithmetic, right? So here you can plug in. So, and this is all big numbers. So we already, in one of our first few videos, we talk about we have the so-called standard libraries. The good news is we already implement, point addition, scalar multiplication. Okay, so now you have the primitives. Once you have these two primitives, you can do tons of other things. Okay, so this is the library we already have, so you don't have to program it. So here we just showing one example here. Uh, as we said earlier, we use elliptic curve operations to re-implement the signature verification. inside a smart contract. Okay. So even before I even dive into this, can you guys think about why we may want to do this in the first place? I mean, doesn't Bitcoin already have the check seek operator built in? Why do we want to? It's almost like a re-implement smart contract. What are the potential use cases or benefits you guys can think of?
I don't know. Maybe there are some other applications in the outside world that can be, let's say, kind of connected using this way.
Okay, that's one way to think about it. Any other guess? Okay. Yeah, I'm not going to have you get wild guess. So there are many reasons, right? First of all, one of the biggest is, if you know about signature verification that's built in Bitcoin, is a very special type. I think it's very limited. One thing is the message, right? For signature verification, you need three things. Okay, what are the three things when you run any kind of like a signature verification scheme? What are the three inputs?
So the message itself, the public key, and basically the result that you want to compute, the signature that
Yes,
you want.
correct. Yes, yeah, the three things, right? So you can almost list here the message, the signature, and also the public key, right? With those three, then without knowing anything about the private key, you can be sure what you can check, right, independently whether the signature is signed by the private key, generated using the private key. Okay. So here's the limitation, I would say, or or sometimes you can see a feature. So the message here cannot be arbitrary. So if you use the native built-in signature verification, the message has to be, you can think about just the transaction. You cannot sign, let's say, the weather data or the price data like the oracles we have seen before, right? It can only be the message. It can only be the transaction, Bitcoin transaction. Okay. But what if you want to sign any other arbitrary message? You cannot do it with a built-in. Okay. So that's one big category. For people who know the history of Bitcoin SV and when BCH split from us, one of the biggest I would say technical differences, they want to add a new opcode just for this, right? Called check data sig or data sig verify. Okay. So they want to verify signature against arbitrary message. Okay. So actually, then with our technique, right, you don't have to invent a new opcode because you can just implement this in a smart contract on top, right? You don't have to change. So that's one big benefit, right? You can sign arbitrary message and then you can verify it, okay, which you cannot do with the native built-in checksig. Make sense so far?
Yes, I think so.
Okay. So the second biggest difference is, so we talked about, let's go back, to the basics. So we talk about, this formula, right? This formula for concrete instance, when you want to use it, you have to define the curve you are working with, right? So basically means it has a given A and given B, okay? But also the curve has some other parameter, right? For example, you may say, I want to work with a key length of 256 bits, or I want to work with this A but different B, right? But here's the thing, the default checksig, everything is hard-coded, right? Because it has to be locked, bounded to a specific implementation. You cannot change, right? For example, here, I think it's this is 7 and this is 0, if I remember correctly. That's what the Bitcoin curve is. But what if I want to use some other curve that's give me some other features, right? For example, some of the curves, they have a so-called, they're very friendly to so-called zero-knowledge proof, right? But the native curve, unfortunately, is not very friendly, meaning it's not very efficient to do zero-knowledge proof, right? But for all kinds of other use cases, so the bottom line is, if you just use the native built-in one, everything is hard-coded. You cannot change. Or another example is, people always talk about, hey, what of a quantum computer? Or in general, right? Because the computing capacity is increasing. So that means given the 256 bits security, so maybe it's secure is super secure today because no computer today can break it. But what if you think about 100 years from now? Oh, there may be some ways to break it, right? So instead of having a protocol change everything about Bitcoin, you can say, hey, why not me? I use this, when I lock my Bitcoin, I lock into my contract. And this contract, the digital signature scheme, I'm using, let's say, 512 bits or even 124 bits, right? So then you don't even have to upgrade, the Bitcoin curve you use. You can just upgrade using the smart contract, which you don't need a protocol change. So that's another big category. So essentially means you are not bounded to a specific curve and all the parameters. You can, because it's just programming. So you can use any kind of configuration you want to have. Okay. Does this make sense?
Yeah, thanks.
Okay. All right. So before I get to the details, I want to just say, how many of you have heard about how do you verify the signature using ECDSA algorithm? The details, has anybody checked into it? Anyone?
No, not in details.
Okay. Okay.
I get it.
So, okay. In this case, let's even before we go to there, let's get to even. Can you guys still see my screen, the browser? Or
yeah.
Okay. Yeah, let's go to the basics. Okay. So here, this is elliptic curve digital signature. So we don't worry about the signing, basic signature generation. We are mostly because in our counter, we are going to verify. So basically, this is the algorithm we are going to use. Okay. So, later on, I'm going to put this on the show notes. So basically, there's a bunch of steps. You basically doing some hashing, and then you compute some big numbers, and then you do here, right? We just talked about this is the point addition, and then this is the point multiplication, scalar multiplication, right? Because we have all the primitives, so that means you don't have to use a new opcode. You can basically implement this algorithm in our script, in S script. Okay, so here I mentioned you have some point addition and point multiplication. So let's go back to what we talk about. Let's go back again and show it here. So if you can follow the algorithm, I think I'm not going to put it side to side, but if you follow that, this is pretty much exactly what you would do if you want to implement the algorithm using any kind of language. Right. So here I talk about scalar multiplication, and then you can add, and then eventually you compare these two scalars. Okay. So basically, this is just simply implement the algorithm we just showed earlier in the slides. So the good thing, as I said before, the hard part, which is all the point arithmetic, meaning addition and multiplication, we're already done. So you can just import our library, and then everything is ready to go. Okay. So this is I just showed one use case, the signature verification, which can be super useful, right? For example, you can use it to have, previously we showed oracles that's based on Robin signature. It's great because it's very easy to verify and efficient in script, but some case, hey, you may say, hey, I don't want to use another cryptography, Robin-based cryptography. I just want to reuse my Bitcoin native keys. I want to sign them and verify them. So that's one way, one use case, right? So you can use just reuse the Bitcoin keys. You can sign and verify the signatures, and then use that as an oracle. Okay, you can reuse keys. That's a pro, but the con is it's a little bit bigger. The script is a little bit bigger than, I would say, a significant bit bigger than the Robin-based ones. Okay, so this is one of the use cases we covered today, and I think I'm going to stop here today. In next week, probably, and also next, I'm going to show more, I think, fancy examples. That's much more complex than this one, and that will be more, hopefully, mind blowing than this one. Just using the primitives of point addition and multiplication. Okay. All right, sounds great. And any other comments before we let you go this week?
No.
Very quick comment. So in this case, in this algorithm, G was the point on the elliptic curve, right? That you multiply, that serves as a basis.
The generator point base.
Exactly, the generator point. And then N is like the big number, is like the prime, the big prime, or what's N?
I think yes, which is called I think it's called is this called, let's see. Yeah, the N is you can think the modulus. Yes, because everything as I'm talking about. Yes, it's all we talk about. We when we show the curve, I kind of say, hey, we are going to gloss over the the details. Basically, it's not going to be consecutive, curve like this. It's going to be dots, right? Because it's all the x and y's in our case is belongs to a so-called a group. It's not arbitrary real numbers. Okay. Yeah, but good point. Yes, these are in reality these are integers.
Yeah.
Okay. Anything else?
Yeah. No, that was everything. Thanks.
Okay. Okay, great. And I hope you have learned something new, and we'll continue our elliptic curve journey next week, and probably next week too. Okay. Hope you'll see you there. Bye-bye.
Thanks.
Thank you. Okay. Bye-bye. Everyone.